Okay, so let's get started then. It looks like we have a good number of people here. So I'm Shane Jenkins. I'm a project manager here at HeroX. I've been assisting this challenge throughout its past year. This is quite a long one, spending over 2 years in development and having two actual phases altogether. So it's really exciting to see these payloads come to fruition. And if you aren't familiar with what they are, you'll be excited in just a moment as we talk a little bit more about what this challenge completed. So let's see here. Today's winners webinar is actually a pretty unique opportunity for you, the audience, to get a glimpse behind these solutions. You're going to learn a little bit about the teams that created these, what compelled them to compete, and what inspired the ideas that they ended up submitting. They quite literally submitted these physical payloads that could be mission ready for launch to the moon. So it's quite an achievement that they created, and you're going to see just exactly what they did to get there in a moment. And I'll say one last thing, which is that NASA quite literally has rocket scientists at their fingertips. So it's exciting to see them looking for genius in all sorts of places, not just from within. That's what we believe the power of crowdsourcing is. And I think you're going to see a little bit of that today. With that, though, why don't we do a little bit of introductions? And while we start this, I'll just say again to the audience, if you're having questions, remember to put them into the Q&A section. And then when we get to our question spaces, we'll be able to filter through them and bring them in. So feel free to submit your questions at any time. With that, though, how about I start with our NASA team? Saba, can you give us a quick intro?
Sure. Hello, everyone. Well, I just want to give a big congratulations to the winners. It's been a pleasure working with you guys for the last 2 years on going from your ideation to your final product. So my name is Saba Bucks. I'm at the Jet Propulsion Laboratory in Pasadena, and I was the technical point of contact for the challenge.
Wonderful. Thanks, Saba. And Kevin.
Hey, I'm Kevin Kempton. I'm from the Game Changing Technology Development Program Office, and I also work in the Prizes and Challenges program. And they're both under the Space Technology Mission Directorate. Right now, I'm out of Langley Research Center, which happens to be the first NASA center where we started our aeronautics program. And so, yeah, this was a new experience for me on this challenge. We've never taken these. Done a challenge where we actually get instruments, flight instruments ready for the trip to the moon. So this is a new experience. We had to go through a lot of new innovative ideas to get this going. So thanks.
Wonderful. Thanks, Kevin. And with that, let's meet our actual teams, the winners of the Honey, I Shrunk the NASA Payload, the sequel challenge. First, we've got Team Sunslicer here, led by the team lead, Phil Jobson. Phil, why don't you kick us off?
Thanks, Shane. Hello, all. My name is Phil Jobson, and I am a spaceflight enthusiast. I live in the wine country, Northern California in Santa Rosa. I have a mad scientist lab in my garage that I use to support my single-man consulting company. My day job is normally telecommunications hardware. Team Sunslicer was created when I met Garrett Jernigan in 2020. At that time, I was begging him for ideas for a payload challenge concept. Garrett conceived Sunslicer and invited his MIT alumni friends, John Doty and Brian Silverman, who's with us today, to join us. They had previously developed educational CubeSats together and done other space projects. John had previously designed a Flight Heritage X-ray spectrometer, was more than happy for us to adapt it to the harsh environment of a lunar rover. Brian pulled a software team together, including the amazing Vadim Gerasimov, co-inventor of the Tetris game, who provided the heavy lifting on the payload software. Countless volunteers, way too many to mention, as well as partners and sponsor companies touched Sunslicer, all with the united goal of creating a space-worthy lunar instrument. Unfortunately, Garrett passed away recently, 2 weeks after the competition winner's announcement. He was very, very pleased with the outcome and one final validation. His passion and inspiration will be missed by all of us. Thanks, Shane.
Absolutely, Phil. And thank you for that tribute to a long and well-deserving man. So thank you. For our second place team, we have Pooley Space with the Pooley Lunar Water Snooper, led by Tibor here. Tibor, do you want to give an introduction to your team?
Yes, thank you, Shane. Good evening from Hungary. Good morning in California. And anytime zone you are on in the world. So Pulley Space is actually will be 12 years old. We started as a Google and X Prize team and started to develop mobility solutions for the moon. But in the meantime, just we have learned that there are a lot of interesting things about the lunar surface, and so this led actually to the idea of the snooper, which will be more explained by David. He is the father of the idea, actually. So you can see our core team. Miklos is our system architect in software design. Matyas is our electrical engineering head, and David is the lead science guy with us. And we had a lot of helping hands, actually, so from Hungary and also from Switzerland. So I will not say all the names here because it would take too long at the moment, but I would like to mention the companies who helped us to create and to validate all the stuff. So this is PCB Design, as the name says. They were helping us to create the electronics part. FPG Art is the hardware part, actually, on the payload. Nanosensors is an academic laboratory at the Central Physics Institute Hungary. They helped us to create the specific neutron sensitive layer, actually, on the sensor what we are using. Electromon just made the Electron, and Kiskutya Kft. Made actually the physical stuff. And just a fun, and the CERN radiation to electronics group helped us to validate actually the principle what we are doing. And the fun fact, Kiskutya is little dog in Hungarian, and Pulley is also a dog breed, and we both are. This is really by chance, it was not on purpose. Both of these teams or these companies have the Pulley as a mascot. So this is our short story here.
Thank you, Tibor. And yeah, the Pulley is one fun dog. Maybe at the end we can pull up an image to show what a little mop dog it is. Sometimes we call it that in the US, a mop dog. Okay. And our third place team here, which is just comprised of these two gentlemen, is Team Microrad. Christian, take it away.
Hello, thank you so much for the introduction, Shane. My name is Christian Howitt. I'm the team captain for Team Microrad. We're definitely the smallest team out of the three that made it to the final round here. Team Microrad is composed of just two people, two lifelong space enthusiasts and current MIT graduate students. I'm Christian Howitt. I got my bachelor's degrees in chemical engineering, physics, and astronomy from UMass Amherst, and I'm currently pursuing a PhD in space systems engineering at MIT. My partner on this project, who couldn't be here with us today, is Joey Murphy. He got his bachelor's in aerospace engineering from MIT, and is also pursuing a PhD in the space systems engineering lab at MIT. So that's our team. We were really happy to be able to participate in this competition and to have made it all the way to the finals. So just want to thank the team at NASA and at HeroX for making this all possible. Thank you.
Thank you, Christian. Thank you for participating. I know that this project took a ton of time on every team, so just one more kudos to all of you for completing it and making it here. For those who don't know, this challenge began with the first phase over 2 years ago, as I mentioned, and these are the final 3 teams among the 12 who had progressed from that first challenge to the second one. So it's been quite a filtering down to get to this point. But before I hop into the individual presentations of the teams, I just want to return to Saba and Kevin real quick and ask a question that I like asking really all of our challenge hosts. And that question is, how would you compare the experience of using a crowd-based prize competition to your typical route of procurement or product design? If I'm correct in understanding this from what Kevin said, this is one of the first times that you've procured payloads in this way.
Well, I'll start really quick. I will say, as we're trying to formulate this challenge, we decided we'll try to run it. This started in January of 2020. I actually looked back, and so it's been a pretty good path to get to this point where we've actually delivered these payloads. But even being an external challenge, we try to run it almost like a flight program. The folks at JPL They developed a common interface document similar to the ones that we do for flight projects. Later on, after the first ideation phase, where the challengers submitted their ideas on instruments, the next phase was based on submitting a instrument development plan, and we made sure they included all the things that are critical for NASA engineering in that development plan. So this didn't duplicate. It really helped because the teams didn't have to duplicate a proposal and then go and develop development plans. And so right from the start, the teams had a good development plan to start with. And so very similar to a flight project. And later on, of course, in the selection on the final winners, it was based on their artifacts, on their test reports, on their design documents, on their interface verification. So, everything that we did, we tried to follow a lot of the guidelines that we do at NASA. And so it turned out very well. And hopefully, the teams really stepped up to the plate. A lot of them want to do like a very agile development, but we tried to balance that with the flight project processes. And overall, I think the way we did this, we'd want to do it again because it turned out very well. And obviously, with 3 out of the 4 phase 2 teams delivering instruments, that's a pretty good record for such a short turnaround. I mean, we really turned the screws on them to force them to get these instruments developed quickly, and they really stepped up to the plate. And so I'll let Saba add her thoughts.
Yeah, just dovetailing with what Kevin was saying, this is the first of its kind that we've ever done for NASA, which is going to the general public in a challenge competition style to get payloads delivered. I mean, truth be told, we had no idea what we were expecting. And so we were trying to employ our flight methodologies of what we typically do for instruments on a very, very accelerated schedule. And I think we are all very, very pleased with the results and the quality of the payloads. So just for the public, I was just mentioning to the teams that we have qualified them at TRL4 at JPL. So all the payloads have successfully passed the vibe test, and they are past the functional testing as well as TVAC. So it's just as good as any other payload that we would have either made in-house or procured outside. So big, huge congratulations and kudos to the team for the substantial effort. So we really appreciate it.
Well put, both of you. And let me just echo those kudos again. These teams have done an excellent job. It's hard to explain just the sheer scale of all the work, procurement, and hours they put into this, but maybe they can give a little bit of a sense of that as we let them speak for themselves. So moving on, let's start with Team Sunsicer here. Phil, just let me know when you'd like me to advance the slides and I'll bring us through your presentation.
All right, thanks again, Shane. Well, hello everyone again. Firstly, what a great picture on this slide for Sunslicer. Many thanks to Trevor Marmon for still allowing us to use it for this project. Okay, next slide. All right, I'm going to give a quick overview of the payload and then follow up with some images and anecdotes that show the journey of development and testing. There are some CAD images there on the left. I'm not going to go into technical details at all, but needless to say, Sunslicer is a complex beast. On the functional side, so why do we care about X-rays? As can be seen in the sun image on the right, the sun is way more interesting when viewed in X-rays. Also, high energy X-ray radiation from the sun can be harmful to astronauts on the moon's surface and to infrastructure on Earth, especially from the active regions that can generate bright solar flares. So our payload's capabilities, Sunslicer can leverage X-ray fluorescence utilizing solar flares as an X-ray flash gun and prospect for minerals. This is useful for creating future habitats on the moon. SunSlicer can also measure the sun's active regions through a clever experiment that leverages rover mobility. And then for free, SunSlicer can monitor X-ray radiation and help keep our Artemis astronauts safe. Next slide, please. Let's start with images of the flight units being fabricated. The pictures on the left are the payload housing being machined. In the middle, you can see the main printed circuit board being integrated with the shutter actuation motor. And on the right are the finished payload, including the thermal protection blanket required for harsh lunar surface temperatures. So, fun fact, the majority of the fabrication of SunSlicer was done in Phil's garage, including the metalwork on a 1,200-pound milling machine. This in-house capability was the secret sauce for developing a complicated payload in such a short time. Okay, next slide. In this slide, the top pics show the evolution of the payload with increasing complexity from a big bundle of wires there on the left-hand side, evolving to the bottom left picture, which is a fully integrated environmental test unit. The bottom middle shows testing the payload in a rented thermal, I'll get that right in a moment, thermal vacuum chamber to emulate the environment of space. And bottom right shows vibration testing of SunSlicer on a shaker table. So fun fact, renting that thermal vacuum chamber and plumbing with liquid nitrogen in my garage was probably the craziest endeavor of the whole challenge for us. Also, the first time I touched a thermal vacuum chamber in my life was unloading it from a shipping pallet into the garage. Okay, next slide. All right, one of the toughest and most time-consuming aspects of the challenge was working out how to protect the X-ray sensor from lunar dust, which resembles miniature shards of glass, seriously. Initially, we attempted to adapt an off-the-shelf optical shutter for the function, but quickly realized it would not perform well in the presence of lunar dust simulant. Hence, a shutter and wiper was conceived and a custom drivetrain and actuator developed to perform the task. We lost a lot of sleep working out how to implement a compact planetary gearbox with massive reduction. It turns out the solution was available to us on a hacker's website. Okay, Shane, let's see if the videos work. These quick videos show how we achieve the reduction with minimal mass, power, and envelope. That first video showed the input stage of the gearbox. The middle video is converting that into an output drive. And then the last video is the full shutter mechanism operating. And for good measure, we even gold-plated the shutter blade, as you can see in the top right. Next slide. The SunSlicer software was developed remotely in Sydney, Australia, Montreal, Canada, and San Diego, California. We figured that controlling the payload from Sydney was at least 5% representative in distance to controlling it on the moon. The software team never actually touched the physical hardware. The top left image captures the joy of the first time we remotely controlled the payload. And that's the Zoom meeting we did it. The lower left image shows the payload dashboard, the user interface with a typical X-ray histogram. And then on the right is the full-up demonstration system for SunSlicer that we delivered to JPL in February. Okay, last slide. Team SunSlicer would really like to thank NASA and the HeroX Challenge team for the unique opportunity. Interfacing with you guys throughout the course of the challenge was really a major highlight for us. We really, really hope that all 3 teams' payloads get a ride to the moon, and that there are future opportunities to interact with those good folks at NASA. Please refer to sunslicer.com for a complete list of credits, payload info, and updates. Thanks again, and to everyone that touched Sunslicer and made it successful. Over to you, Shane.
Wonderful stuff. Thank you, Phil. Looks like we've got time for a question or two here. First one, which is coming more generally, is just wanting, excuse me, was that I wanted to know, how did your team deal with procurement issues, since so many teams, in fact, every team, struggled with both supply chain issues and COVID closures? What advice would you have to any other teams that are looking into working out procurement from an amateur perspective?
Yeah, it's a tough one, Shane. You've got to get in front of the curve. I was winding down a commercial project at the beginning of last year, and I was getting hammered on that project on supply chain. I was adding redundancy to printed circuit boards to deal with parts going obsolete on a daily basis. So I guess that that was the clue. So yeah, right in the first couple of months, nailed down the things that were critical and got them in the pipe as soon as could.
Absolutely. And then another question we have here is someone wondering what memory or experience stands out to you the most from this time? Just what's your favorite memory from this from this experience?
It would be too hard to pick one. It was just one continuous activity of willing things into existence. There's probably 5 serial miracles that had to happen for a functioning Sunslicer, and it just constantly willing it into existence. That's really what it was. Borrowing and stealing everything.
Whatever it takes. Sounds good. Well, okay, I think it's about time we move on to the next team, which is Team Pulley, or Pulley Space, excuse me. Tibor or David, you want to take it away?
I will make a very short start, and I will pass over to David, actually, so because he knows the best, and actually, again, as I mentioned, this came out from his insisting to get into this challenge, because we might start with the note that as we learned about the challenge 2020 in April or so, David came and said, okay, hey, this is good, let's try to do our idea how to get neutrons counted on the moon surface. And I said, I don't believe in that, and I can also cite Matyash. He was even harsher, so said this is just a waste of time. But when they said, okay, let's check this one, and so the idea just was born, and then we just worked out the stuff, and we had a lot of such nice moments, actually. But let's go to the next slide, and you will see what is actually about, what is the Pulley Lunar Water Snooper. As I mentioned, we call it snooper because Pulley is a dog, actually. So he's snooping or sniffing for water on the moon. I would pass over right now to David. He will explain what is it about, and let's see how did we manage to get to the final part of delivering the 3 pieces, 3 hardware to GPL. David, it's your turn.
Thank you very much. Can you hear me well?
Yeah.
Yes.
Mm-hmm.
Okay, great. Thanks for the introduction, and I would like to talk to you about neutrons and water on the lunar surface and how these are connected. This slide looks a bit too scientific, probably, for most of the people, but don't be afraid. So I won't go into scientific details, and just introducing the concept on a high level. So we have 2 major knowledge gaps on the moon. We would like to address, we wanted to address with our payload. As Tibor and Mátyás wasn't believing, as Tibor mentioned, that it's possible that, but fortunately, I didn't believe them. So we made.
I'm a believer in the meantime.
Yeah. So the first knowledge gap we would like to address is that we don't know too much about the neutron environment, about the lunar surface, because the data is already a bit limited, and so there are still a lot of unknown questions regarding this. Also, another important knowledge gap, and we know even less about this, is how much water ice is on the moon, in the different lunar regions, and so what is the content, water content of the soil, and how it is distributed on the lunar surface on a smaller scale and also on a larger scale. So, and fortunately, these two knowledge gaps are actually connected, and we can use neutrons to find and measure the water content of the lunar soil based on neutron spectroscopy by measuring and counting neutrons, detecting neutrons. So yeah, so our goals, yeah, we have three steps, basically, three main goals. First, is we would like to count the low energy neutrons, namely the thermal neutrons and epithermal neutrons separately. So thermal neutrons are the lowest energy neutrons, and epithermal neutrons is a bit, they have a bit higher energy, but still low energy. So we need to count these two quantity, the number of thermal and epithermal neutrons separately, and with this we already can characterize the neutron environment and tell a lot about it. And next, if based on the ratio of these two quantity, so the count numbers of thermal and epithermal neutrons, we can tell a lot about the water content, because the higher the water concentration of the surrounding lunar soil below us, the higher the thermal neutron flux and the thermal neutron count rate, and lower the epithermal neutron count rate. So we can say that the energy distribution of neutrons coming out the lunar regolith is actually characteristic to the local soil composition, and it's really highly depending on the hydrogen and therefore the water ice content of the soil. So basically, this is the most useful and most important application of neutron spectroscopy on the lunar surface, that we can, by simply counting thermal and epithermal neutrons, we can tell, okay, probably there is water here, and we can even measure the concentration of water. And okay, but up to now we are just measuring at one single location. But what if we can move our instrument detecting neutrons to another location, for example, with a rover? So if with the rover we can scan an area or take a longer route, we can continuously monitor and count the neutrons. And basically we can make a map of water resources or water deposits and know the spatial distribution and amount of water in many different smaller area or points on the lunar surface, which will be extremely useful if you would like to mine and utilize this amount of water ice on the moon. And so the neutron spectroscopy and detecting neutrons on the moon or around the moon is there is nothing new in this concept. But how we can do this with very small rovers, with very small payload instrument, compliant with all the NASA requirements. And we got the inspiration from space telescopes and imaging sensors of space telescopes, because there are already many image sensors in space used by astronomers, for example, in Hubble Space Telescope, which is the best known, or James Webb Space Telescope. And they have many image sensors, and they are actually sensitive not just to light, but also to ionizing radiation. So each time a cosmic ray is passing through the sensor, we can see on the images, and astronomers have to remove these noise basically. But we figured that we can use this this noise and spurious events just as signal, and we just need to make it neutron sensitive. And then we can go to the next slide. So based on this concept, we have developed from scratch a neutron spectrometer with image sensors, using 3 image sensors, which are the same image sensor and sensitive to light, but also because they can capture the images of cosmic rays ionizing radiation. We are using them to count particles with it, not measuring light or taking images, but measuring or detecting ionizing particles with the sensors. So we in this central image, you can see the as we remove the cover of our payload, polylunar water snooper, we have the two image sensors which has a special neutron sensitive coating and sensitive to thermal and epithermal neutrons. And we have a third reference sensor which doesn't have a coating, but sensitive and sensitive to cosmic rays and all the background radiation, so we can use as a reference. We also have a filter, so we can make a difference. We can discriminate and separate thermal and epithermal neutrons. And also we have a thermal shielding, thermal neutron shielding to stop thermal neutrons reaching the sensors from above, falling on the payload or coming from different directions. And we also have an FPGA just to count, run the sensors, take images and count the neutrons. And you can also see here a few examples of neutrons captured actually with the image sensors, but I will come back to this a bit later. You can also see here a very nice photo of our fully assembled prototype of the PLWS. We have also delivered to NASA. And I'm happy to say that we made a lot of qualification and functional tests of our payload, and all the tests have been passed. So we heated up in a climate chamber up to really high temperatures, and it was still working. We also vibrated really hard to see if it can survive the rocket launch, and our payload instruments have passed the vibration test as well. Also, we made electromagnetic interference and electromagnetic compatibility tests, and it has been also passed. So our payload is really functional, and it can survive and function in the on the lunar surface as well. And finally, probably the most important test campaigns we made was the neutron test at CERN with an American neutron source. And with this, we had many fast neutrons and thermal neutrons bombarding continuously the PLWS. And I'm happy to say that it was fully functioning as a neutron spectrometer, and we could detect both thermal neutrons, epithermal neutrons, and fast neutrons. As we changed the setup, the neutrons and the neutron count rays changed as expected. And at this point, we made these nice images of the detected thermal neutrons. So we basically, yeah, it's really nice that in this very short amount of time, we managed to develop our neutron spectrometer from scratch and also characterize it. And the tests have showed that it could measure and find water ice on the lunar surface based on these concepts. And the next slide, please. And with this, I would like to thank to NASA JPL and HeroX for this really nice opportunity. So without NASA and HeroX, we could not develop and make this payload. So, and yeah, here you can see a nice photo about the payload handover at the NASA JPL in February, as Tibor and Mátyás delivered and handed over the 3 working flight-ready PLWS payload instruments, and we hope that it can make it to the moon and detect water there. So thank you very much, and thank you for your attention.
Absolutely. Thank you, David. I think we have time for just one question right now for your team before we come back to general questions. This is open to anybody on your team, but someone was wondering, with a team that's so large and spread across so many countries, how did you find the necessary talent for a project like this? And what advice do you have for coordinating teams of your size?
This is a good question. Yeah, we had a really big collaboration at the end, fortunately. So, of course, Spoolie Space alone could not develop this payload, but we really need a lot of collaborators, companies, scientists to help us out. And yeah, it was not an easy task to coordinate, but actually we at Spoolie Space already had some experience about the collaboration and remote working and working together with other teams. So it wasn't new for us, but yeah, it was challenging. Of course, to coordinate all of this, and yeah, we needed good skills for project management on every level.
Sure thing, yeah. Well, thanks, David. We'll hear some more from the teams, all the teams at the end, but let's move on to our third team and final team here, Team MicroRad. Go ahead, Christian.
Thank you, Shane. So MicroRad was developed in response to one of the greatest hazards associated with human spaceflight, and that is radiation in space. So when you leave the surface of the Earth, and particularly when you leave the protection of Earth's magnetosphere, astronauts and also instruments as well are subjected to galactic cosmic rays, very high energy radiation coming from the exploding cores of distant stars, and also to solar energetic particles, which are lower energy, typically protons and helium nuclei, but which can still contribute to that radiation dose. And so this can contribute to a number of poor health outcomes for astronauts, and also can affect how well instruments can be expected to operate in space and how well they can potentially, how long they can continue to operate. So this hazard is well acknowledged by NASA. And in the case of the Mars Science Laboratory, they flew the Radiation Assessment Detector, RAD, which you can see on the right here. And this is an instrument that's able to characterize fairly broadly the radiation environment, both in flight to Mars and also on the surface of Mars. So that's giving mission planners a lot of really key information that they need to know about how they need to shield spacecraft that could potentially transport future astronauts to the surface of Mars. And it's also very helpful to know with regards to how you design shielding, for example, for electronics. So essentially what we wanted to do is implement many of those same capabilities, but to do it smaller, cheaper, and essentially we want to do that by implementing and taking advantage of some novel technologies, which have really only come into their own in the time since RAD was developed. Next slide, please. So the final solution we came up with is microrad, basically the micro-sized radiation assessment detector. And you can see that on the right on our little test interface board here. And so this is composed of a scintillator, which when struck by radiation produces a pulse of light. Then there's silicon photomultipliers, which convert the light into an electrical pulse. And then we have processing electronics. And this is sort of the same basic general architecture as RAD or as many other instruments. It's just we implemented it with different materials and different approaches. So it's sort of the approach that we took here was not so much reinvent the wheel as it was make the wheel out of a new, better material or with a new, better process. So for future teams looking at participating in challenges like this, where the schedule is very constrained and the budget is tight, that would kind of be that might be my first piece of advice, or the first lesson that we learned. Basically utilize an existing instrument architecture and then make it better by improving it gradually rather than trying to reinvent the wheel. The second piece of advice I might offer based on our experience, identify the major drivers of design complexity and swap early. So it's one potential approach is basically decide you're going to optimize every single component of the system. But when you're on a very short schedule and a tight budget, you really can't afford to take that approach. So instead, it's much better if you can identify the components or the aspects of your design that are major drivers of swap complexity and cost, and put your effort towards optimizing those as early on as possible. Third piece of advice, leverage new off-the-shelf materials and components and use those to reduce complexity. So as I mentioned, we use silicon photomultipliers, which are a device which has really only become commercially viable in the last 10 years and has really improved gradually just in the last 3 to 5 years or so. And so we use those to replace a photomultiplier tube, which is how the issue of converting the light pulse from a scintillator to an electrical signal is typically solved. And so that allowed us to reduce the size, weight, cost of that we would typically encounter using a photomultiplier tube. And additionally, the silicon photomultipliers being solid state are much less fragile than the photomultiplier tubes, which are made out of glass. Fourth piece of advice, I'd say, don't give up flexibility when you don't have to. So I'm in a PhD program for space systems engineering, and the typical approach that you take is define all the requirements for your payload or your project or your system as early on as possible, identify how you're going to verify those requirements, and then move on to the design process. So it's sort of like a cascading waterfall that, for the most part only goes in one way, in one direction. And so that approach, while it's really good for breaking down a very large, complex problem like building a space shuttle, for example, sacrifices a lot of flexibility early on. And so I think what really helped us be able to complete the payload and complete it as well as we did was hanging on to a little bit of flexibility to later points in the project, just because every bit of flexibility that you have in your design is a potential solution to another problem that you may not have encountered yet. And then I'd say the final thing to remember is that every design or management decision has trade-offs. This is particularly true when you're working with a firm fixed contract structure. you don't really have the option to extend your schedule or ask for a cost overrun, as is typically the case for more traditional aerospace. So you have to understand in very concrete terms that every design and management decision that you have has trade-offs and consequences that need to be considered, and you can't really just push the consequences off into the future and deal with them later. So given that I think Kevin mentioned that there's a lot of interest at NASA in doing a future competition along similar guidelines, I just wanted to sort of put down the lessons learned, and maybe people who are participating in the webinar and might be future applicants to these competitions could potentially learn from those lessons. Thank you.
Yeah, thank you, Christian. That's actually incredibly helpful. What's funny is you've preempted some of the questions that have been coming in for you, but let's see, one here that remains is, can you just specifically or personally speak to how you were balancing that student challenge balance, student and challenge responsibilities? I know that both of you were in PhD programs, which are quite intensive. So where did you find the time to work on this?
It was definitely a major driver of it. It definitely wasn't easy, I'd say. At the same time, there were certain advantages coming from being a student. We had access to a lot of equipment and facilities and expertise that we couldn't get otherwise. Along the way, we were able to ask people for help both within MIT and also at some national labs, and that really helped us to move the design forward. Mm-hmm. But there was definitely some issues with time management, and sort of how we approach that is basically, for the most part, during the week it was PhD work and the responsibilities that came with that, and then trying to work on the payload basically over the weekend. And so trying to sort of compartmentalize a little bit and just try to keep on the schedule by compartmentalizing and setting very realistic expectations for what would happen on what deadlines, and basically just trying to keeping things moving forward.
Interesting, thank you. Well, with that, I'll stop our screen share here and bring us back to our panelists. And I'll take this as an opportunity to remind those watching that if you have any questions, please submit them in the Q&A section of the Zoom webinar. We'll be looking at them in the background and trying to filter out the ones that, the ones we can ask. So if you want to ask a specific panelist something, be sure to include who that panelist is with your question. In the meantime, though, why don't I ask the people who are on this call, our teams here, do you have any thoughts on each other's presentations? You all were kind of working siloed from each other for a long while, and then you've recently came in contact with each other over the past few weeks. Any thoughts on each other's work?
I'll jump in. I think the projects are all incredible. This was an impossible task, and to actually get 3 finishes is nothing short of amazing. So I just want to congratulate the other teams, but yeah, the finished products look awesome.
I just can join Phil to your opinion, so that it's really amazing to see, and special congrats to Christian and his teammate actually, because so a small team was able to put together all this fine stuff. It's really great. So the other teams had more resources in that sense, so more collaboration, so which brings of course a little bit different problems as well, so how to coordinate that. But anyway, I think as I mentioned, I'm really a believer, so that it was a great run for all of us, just in 1 year from concept to reality, and this is just really great. Thanks for NASA, thanks for HeroX, and thanks for you both teams as well, just inspiring us to go forward.
Yeah, I'd just like to thank Tibor and Philip. I really appreciate the sentiment. I really enjoyed your presentations as well, and I'd love to learn more about your payloads. And I don't know if you have any plans to share additional design documentation or additional information, but I'd love to learn about your payloads and how exactly you implemented your designs, and it's just great to learn from people with more experience and additional backgrounds that are different from my own.
Sure, keep contact. Let's get contact. We have each other's email addresses, so this is great. And Phil, we will come to California to take a wine if we are happen to be there.
Phil's been promising tours of the wine country, so you better pony up, Phil. I'll show up at your house.
Absolutely, we've got the good stuff here. And Christian, yeah, we welcome any conversations. Feel free to reach out.
Thank you.
Maybe just one short note. So as I mentioned, so we are working also on a rover, which is around this 10-kilogram rover class, and we have just checked how much micro payload we could host on that rover, and we have at the moment in our prototype places for at least 2. So not only for the snooper, but maybe for the slicer or for the micro red. So we would like to test it, and let's check this idea further.
Wonderful.
Covering all the bases. Well done, Tibor. Well, let's see here. I think we've had one other question come in from the audience, and this is more of a general one, so anyone who wants to hop in can join this, but they were just curious about what surprised you with this. There was certainly a lot of unexpected things that arose for each team, but does anyone have something that they really didn't see coming?
So I have something. I'm sure it probably sounds like a broken record if you're in the space electronics community at this point, but when we originally submitted our proposal, one of our expectations was that all the components we were using were off the shelf, things you could order from DigiKey, and basically you could place an order and have it on your doorstep, a week later at the most. We sort of got an awakening roughly May or June. Basically, we went through a lot of the paper design work and then turned around to go and order components, and suddenly found that we were contending with some long lead times that we hadn't expected, because even February or March or so, everything was in stock. So that was definitely a major unexpected hurdle that we had to overcome. And I definitely advise anyone trying to build electronics in this current environment to begin your component placement, placing component orders as soon as possible. Even maybe to the point of delaying actually laying out your circuit board until you've actually got the components in hand.
I'll just echo Christian's sentiments there. My advice, don't try and procure a brushless DC motor in a 6-month time frame. It will put you in a mental institution.
We had also a moment of shock, let me put in that way, because at the beginning we ordered just I remember 3 or 5 FPGAs for testing, and then I wanted to order the next round of FPGAs. There's nothing on the market, and it was just a miracle. I just went back to one of the vendors, and it was 12 pieces. I don't know, from nowhere. So it was just a piece of luck for us that we could go further with that.
Maybe another
thing which was which was a positive stuff actually for us. We learned in the mid-time approximately that the same techniques what we are using for detecting water ice or hydrogen on the moon can be used here on Earth to monitor soil moisture. And this was really a surprise for us that the same physical principles are working, of course, a little bit different because the environment is different. And this brought us to the idea to check some spin-offs actually from the snooper. And we are working right now on this agricultural application. We have won an ESA, European Space Agency tender to work out the business case and the prototype. And also CERN is interested in the snooper just to monitor the Large Hadron Collider neutron environment. So this was a very positive surprise for us that we can go on that.
That's exciting
I
stuff.
was just going to add in a story real quick on the procurement of the specific aluminum alloy that JPL recommended for their instruments, and obviously one of the teams couldn't find that alloy, and so being very mindful, this was a competition. We reached out to the other teams if they could help get this alloy or find a source, and both teams, even though it was a competition, they both offered to help get that alloy and find a source for it from what they had done. So yeah, with the procurement and the sport, I call it sportsmanship, it was just fantastic for the teams. I was very impressed to see how they handled that.
Well put, Kevin. It really was a challenge full of surprises in every way, positive, difficult, and yet affirming at the end, like you mentioned. With that, we've only got about 3 minutes left here, so why don't we head towards wrapping it up. The final question I usually like to ask of our sponsors again is, now that you've got your solutions, what's next? And is there anything like this in the pipeline? I think there's some people wondering if they could participate in the future.
Well, I could say that right now, so like I mentioned before, we just finished all the functional testing for the payloads. So we're in the process of doing accommodation study. So that's in the work, and that's separate from the challenge. So we'll announce that at a later date. In terms of follow-on coming in through the pipeline, I'm going to defer that one to Kevin. I think this was a really good mechanism, a fantastic mechanism, and definitely there are some lessons learned here in terms of how to stage this, how to get the requirements to teams, and potentially give them a little bit more time and flexibility. So definitely would like to do this again at a later point. I'll defer to Kevin and see if he has any insight on when we would have a follow-on.
Yeah, I'll just add real quick that this truly is game changing. These instruments are literally an order of magnitude less mass, volume, and power, and they're also probably an order of magnitude less cost. And so it's really game changing. Opens a lot of doors on that. As far as this is a disruptive thing. We're going out. We're not developing, before we had the options of either having a contract or doing the development in-house. And now this is like a third option. We have the option of having an open competition in order to obtain products. And this being the first one, the fact that we've gotten what appear to be 3 successful instruments out of an open competition, it's going to open a lot of eyes as far as being able to have a third alternative to procure items for the government. And so I think it breaks a lot of ground for what we're doing. And I think we'll want to do it in the future. One of the things, like I said, NASA likes to have control of development. And I think Christian had mentioned that, yeah, things come up. And so during this challenge, we looked at development plans, but we didn't really interfere with how the teams, did their development in the middle there. And at the end, we expected some artifacts of the quality of their products. But it's hard for NASA when we like to have hands-on visibility on what's going on in the development and letting teams go out and do it their own way. But we did have tag ups throughout and status checks to make sure everything was going. But this truly is a new way of doing things, and it seemed to work. So I'm really hopeful that we'll be able to do this in the future more often.
Great stuff. Well, thank you all again for attending. We're just at time here. And let me extend one final congratulations from HeroX's team to all 3 of you. This has been so fun working with you over the past 2 years, and it's great to see the stuff that you've all created. So thank you. And if the audience can join me in giving a virtual round of applause.